Good day, everybody. How are you all? Today we are going to talk about central limit theorem for proportions. So here I go. Construct the sampling distribution for a sample proportion. In a population, the proportion who have a certain characteristic is called the population proportion. The population proportion is denoted by P. In a simple random sample of any individuals, let X be the number in the sample who have the characteristic. The sample proportion is P hat. That small symbol on top of P is called P hat is equal to X over N. So X is the number of successes or the number of P sample number in the sample who have the same characteristic. Sometimes that is called number of successes, and N is the sample size. A computer retailer wants to estimate the proportion of people in a city who own laptop computers. She cannot survey everyone in the city. So she draws a sample of 100 people and surveys them. It turns out that 35 out of the 100 people in the sample own laptops. Sample proportion P hat is then, because 35 own laptops out of 100, sample proportion P hat is 35 out of 100 or 0.35. The proportion of people in the entire city who own laptops is the population proportion P. If several samples are drawn from a population, they're likely to have different values for P hat. Because the value of P hat varies each time a sample is drawn, P hat is a random variable and it has a probability distribution. As you can see, the rectangle represents the population, and we are drawing different samples of the same size, and they all give us different values of P hat. Suppose I have 30 samples of size 100. Then I will have 30 values of P hat. I can divide this P hat, 30 values, into groups of, say, 5 of equal width. On top of each group, the groups are on the horizontal axis, P hat values are on the horizontal axis. Groups of P hat, 30 samples, I divided them into, say, six classes with equal interval width. So what will happen is on top of each group, we will draw a vertical rectangle. That vertical rectangle, the widths of the vertical rectangles at the base are same for all the rectangles, but the heights are different. What are the heights? The heights are the relative frequency, or what proportion of the total of 30 samples fall in each of the six groups. So the height gives the relative frequency. And we have vertical bars equal with different heights. Now, if we join the top roofs of these vertical rectangles, adjacent rectangles, you will get a smooth histogram. And that is called the probability distribution of P hat, which is the sampling distribution of P hat. Consider tossing a fair coin 5 times. This produces a sample of size n equal to 5, where each of the item in the sample is either a head or a tail. The proportion of times the coin lands on heads is the sample proportion P hat. The probability that it lands on head each time is 0.5. Therefore, the population proportion of heads is P is equal to 0.5. Next, we look at all 32 possible samples that can be constructed. Remember, we are tossing the coin 5 times, and there are 32 possible samples. And these are shown as that. Notice you have a sample, one column, and the corresponding p hat. P hat is a sample proportion. For example, if you look at the first sample, T, 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 5 T's, because the coin is tossed 5 times, we did not get any head at all. So P hat, which is a sample proportion of head, in this case is 0. For the next one, we got one head. So the sample proportion of head in this is 1 out of 5 or 0.2. The table displays all possible samples of size 5 and their sample proportion P hat. The mean of all values of P hat is, now if we put this 32 values 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4. Okay, 32 values of p hat, the p hat column in a L1 in the calculator TI-84. We will get the sample, the mean of all these p hats will be equal to the population mean, which is 0.5. However, if you get the standard deviation of this, and this is a population, so we are interested in sigma p hat, we will find it is 0.2236. Okay. Next, we compare these values to the population proportion. Remember, population proportion is 0.5 and the sample size 5. So, in the previous table, the mean of the sampling distribution is mu p hat is 0.5, which is same as the population proportion p equal to 0.5. This relation always holds. The mean of the sampling distribution of p hat is denoted by mu p hat and equals population proportion. Thus, mu p hat equal to p. The standard deviation of the sampling distribution, sigma p hat, as we indicated in the previous slide, is 0.2236. It is not immediately obvious how this is related to the population proportion p and the sample size n. However, note, however, that sigma p hat is 0.2236 is square root of zero point 0.5 times 1 minus zero point 0.5 and divided by 5. What is 5? 5 is a sample size. What is P? Population proportion is 0.5. So the formula for the sigma P hat or the standard deviation of the sampling distribution of P hat is given by square root P times 1 minus P over N. The soft drink cups at a certain fast food restaurant have tickets attached to them. Customers peel off the tickets to see whether they win a prize. The proportion of tickets that are winners is P equal to 0.25. A total of N equal to 70 people purchase soft drinks between noon and 1 p.m. on a certain day. Let P hat be the proportion that win a prize. Find the mean and the standard deviation of P hat. Now we know the mean of the sampling distribution of P hat will be equal to P population proportion, which is 0.25. And the standard deviation of P hat is square root of. Now, how do I get the square root? So if I have TI-84, I press second button and then x square, which is in the first left column, halfway down. Second x square gives me the square root. Inside the square root, 0.25, left parenthesis, 1 minus 0.25, because P's population proportion is 0.25, then whole thing, the numerator is divided by 70, all happening inside the square root. And then you hit enter. And the answer is 0.0518. That is the standard deviation of P hat. Find mu p and sigma p hat if n is equal to 20 and p is equal to 0.82. Then mu p hat will be equal to population proportion equal to 0.82. And sigma p hat will be second x square square root. Inside the square root, p is 0.82, then left parenthesis 1 minus 0.82, right parenthesis divided by n is 20, and hit enter. And the answer is 0.086. Yep, 0.08591 and 0.82. Okay, so our answer matches. Moving on, the probability histogram for a sampling distribution of p hat for the proportion of heads in 5 tosses of a fair coin is presented. We can see that the distribution is reasonably well approximated by a normal curve. This is the sample proportion of heads on the horizontal axis and relative frequency of probability on the vertical axis. As I explained, that we have divided the sample proportions into 1, 2, 3, 4, 5, 6 groups of equal width. On top of each of these groups, we have a vertical rectangle. The height of the rectangle is the relative frequency or the proportion of the sample, proportion of total sample that fall in each group. Okay. And As I told before, if you join the top roofs of these vertical rectangles, you get a bell-shaped histogram. Okay, so this is for 5 tosses. The experiment is conducted again, but with 50 tosses of a fair coin. As we increase the number of tosses, the sampling distribution of p hat is more closely approximated by a normal curve. So going from the top to the bottom, the only difference in the top is we are tossing the coin 5 times in the top. In the bottom, the second one, we are tossing the coin 50. What has happened? The sampling distribution of p hat is still bell-shaped, but it is more closely related to a bell-shaped histogram rather than the top one where the sample size was 5. When p is equal to zero point 0.5, the sampling distribution of p hat is somewhat close to normal, even for a small sample size like n equal to 5. When p is close to 0 or close to 1, a larger sample size is needed before the distribution of p hat is close to normal. In our case, p is 0.5, so we are fine. Even with a small sample size of 5, we got a bell-shaped histogram for the sampling distribution of p hat. A common rule of thumb is that the distribution may be approximated with a normal curve if whenever n times p, n is number of sample size, p is population proportion of success, n times p and n times 1 minus p are both at least 10 means greater or equal to 10. We now state the central limit theorem for proportions. The central limit theorem for proportions, let p hat be the sample proportion for a sample of size n from a population with population proportion of p. If n times p is greater or equal to 10 and n times 1 minus p is greater or equal to 10, then the distribution of p hat is approximately normal with mean mu p hat equal to p and standard deviation sigma p hat equal to square root of p times 1 minus p divided by n. Decide whether it is appropriate to use normal distribution to find probabilities for p hat. Now we look at, first we will do n times p, which is the top one on the left is 20 multiplied by 0.7 is 14. N times p is greater than 10. How about n times 1 minus p? That will be 20 multiplied by 1 minus 0.7, which is 0.3. So 20 times 0.3 is 6. That is not greater than 10. Therefore, we cannot use a normal distribution for the sampling distribution of p hat. Okay. Let's take a look at the one at the bottom right corner. Simple random sample of size 1000 is drawn from a population with population proportion of 0.3. First, we do n times p, which is 1000 times 0.03 is 30, greater than 10. Then we do 1000 times 1 minus p, which is 1000 times 1 minus 0.03, or 1000 times 0.97, which is 970. That is also greater than 10. Since both n times p and n times 1 minus p are greater than 10, we can use a normal distribution for the sampling distribution of p hat. Use the central limit theorem to compute probability for sample proportions. So basically we will use our calculator. According to Harris poll, chocolate is the favorite ice cream flavor for 27% of Americans. If a sample of 100 Americans is taken, what is the probability that the sample proportion who prefer chocolate is greater than 0.3? Notice the population proportion in the first line is 0.27. So P is 0.27 means the mean mu P hat is equal to also 0.27. But let's check N times P, which 100 times 0.27 is 27 greater than 10, and 100 times 1 minus 0.27 or 100 times 0.73 is also 73, that is also greater than 10. Why do we check these two calculations? Because we want to make sure that we can use a bell-shaped distribution for the sampling distribution of P hat. Next, we are going to compute mu P hat. I told you mu P hat equal to P equal to 0.27. How about sigma P hat? Sigma P hat is second x square, gives me the square root. Inside the square root, 0.27 is P. then parenthesis 1 minus 0.27, right parenthesis, divided by sample size 100 is equal to 0.04439. Okay. Now we want to find out what is the probability on the right, or the area under the normal curve on the right of 0.3. Okay. So second, verse 2. So I'm starting my calculation from 0.3, my lower end. My upper end is a very large number on the right. So for that, I type upper 1, then second button and comma button, which is on top of 7 button, to give the small capital E, then 99. My mean I have already calculated is 0.27. My standard deviation is 0.044396. And then I go down on PEST, hit enter, and the answer is 0.2496. So the probability of that the sample proportion of those who prefer chocolate is greater than 0.3 is almost quarter, 0.25. Approximately 60% of eligible voters in a recent US presidential election voted in a recent US presidential election. So if a sample of 88 eligible voters were polled, would it be unusual, less than half of them, that means less than 44, okay, or less than 0.5, okay. So first we check out n times p, 88 multiplied by 60%, 0.6, is 52.8, that's greater than 10. And 88, then left parenthesis 1 minus 0.6 in right parenthesis. So inside the parenthesis, so first I typed 88, then left parenthesis, then inside the parenthesis 1 minus 0.6 I typed, then I close the right parenthesis and hit enter. That's 35.2, that is also greater than 10. Now we will find sigma p, mu p hat and sigma p hat. Mu p hat is equal to p equal to 0.6, and sigma p hat is second x square, gives you the square root. Inside the square root 0.6, left parenthesis 1 minus 0.6, right parenthesis divided by sample size of 88 is 0.052223. Okay, find the, so then they ask what is the probability less than 50%, less than 0.5. So we are starting our calculation from the left end of negative infinity. So second, verse 2. Now the lower boundary is minus sign next to the enter on the left, then 1, then second comma gives you the E 99, and the upper is we are stopping at 0.5. Our mean is 0.6. Our standard deviation is 0.052223. And I go down to PEST, hit enter, and enter. And the answer is 0.0278. Notice this probability is less than 0.05. And therefore it is unusual for less than 50% to vote. Okay. Another problem. General Social Survey reported that 56% of American adults saw a doctor for an illness during the past year. Sample of 65 adults is drawn. What is the probability that more than 60%? We are on the right of the 60%. But first, let's check n times p. So my n is 65 multiplied by p is 0.56 is 36.4, greater than 10. Then I will do n times 1 minus p. Again, my n is 65, left parenthesis, 1 minus 0.56, and then right parenthesis. So inside the parenthesis, 1 minus 0.56, and hit enter. And that is 28.6. That is also greater than 10. Therefore, we can assume the sampling distribution of p hat is bell-shaped. And we want to find the probability or the area under the normal curve to the right of 0.6. So second, verse 2, I'm starting from 0.6. My upper is a very large number on the right, so 1 second comma gives you the E 99. My mean is the population proportion is 0.56. Right? And what about my standard deviation? I have not yet calculated it, but I can achieve it inside that sigma. So bring the cursor on the right of the colon in the sigma line and then press second excess square to get the square root. Inside the square root, remember the first is the p, 0.56. Then left parenthesis, 1 minus 0.56, p times 1 minus p. Then divided by the sample size of 65. Okay, and then hit enter. Okay, so it will automatically calculate the sigma um, when it does a calculation using that formula. What is the probability that more than 60%? So we are on the right of 60%. And that probability, you have remember on PEST, you have to hit enter twice, is 0.2579 or 0.258. Would it be unusual that more than 70 now? So second verse 2, more than 70 means we're starting from 0.7 and we are on the right of 0.7. Nothing else changes. We go down to PEST, hit enter, and the answer probability is 0.011, which is less than 0.05. So it would be unusual if more than 70% saw a doctor. Why? Because the probability is less than 0.05. So I stop here today. If you have any question, comment, please write me a note. I'll get back to you as soon as possible. If you like this video, please give me a thumbs up. I really appreciate that. And that will motivate me to produce more useful videos. And if you like this video, share with your friends. You and your friends, please subscribe to my channel by hitting the red subscribe button at the bottom right corner, and also hit on the bell button because that will notify you every time I upload a new video, which I do almost every day. So you and your friends, please subscribe to my channel by hitting the red subscribe button. And thank you for taking the time to watch me, and please do not forget to watch me tomorrow when I'll be back with another interesting video. Thanks. Take care. Have a nice day.